In this video I talk about numerical integration in 1, 2 and 3 dimensions. Please open the example script, example numerical integration. It can be found in the folder examples 6 in TIS. I start with defining the function to be integrated in symbolic form, so we can obtain an exact value of the integral and then assess the relative error of various numerical integration methods. The function is a simple damped harmonic oscillation. I convert it to a function handle and I choose the values of a and b to be 2 and 0.5. And I define the integration interval. The integration runs from 0 to 8. Let's plot the function. I use fplot to plot the function. I label the axis, I print a title. So now we can see the function, the graph of the function in the figure 1 in the window at the right hand side. Now let's compute the exact value of the integral from 0 to 8 by symbolic integration, and I store the exact value in the variable I symb. You can see the value displayed in the small window. Okay, now I specify a function handle that depends only on x with the current values a and b. The simplest way to compute such an integral is probably the trapezoidal rule. It's simple, fast, but not very precise, as we'll see in a minute. The precision, of course, depends on the number of grid points. Let's start with 100 grid points in the interval. And we can approximate the integral by the function trap-z for trapezoidal. And we can compute the relative error of this result by subtracting the exact value and dividing by the exact value, and we see the relative error is in the order of 2 per mil. Let's take 10 times as many grid points. So we define a new grid with 1,000 points, and the relative error drops to about 2 times 10 to the minus 5. If you want to have an approximation with a smaller relative error, there are two possibilities. You can use the function quad or the function integral. Let's try quad first. You see the calling sequence is always the same. Function handle integration limits. The relative error is now below 10 to the minus 7. And the other function is called integral. And this has a relative error of 0, so I suspect that integral in this version of Matlab does also symbolic integration if possible. In previous versions of integral, I've seen a relative error which is in the same order or smaller than the relative error of the function quad. Let's now pass to integration in 2D over an area in the xy plane. Again, I first define the function in symbolic form, then convert it to a function handle. And now we want to integrate this function, e to the minus x squared minus y squared, over the unit square. So x runs from 0 to 1 and y runs from 0 to 1. And this can be done by using the function integral 2. The first argument is a function handle. Then we have the limits in x, 0, 1, and then the limits in y, 0, 1. We can also obtain an exact value by symbolic integration. So we first integrate over x, and then we integrate over y. And we get an exact value in terms of the error function that I talked about in the last video. So we can now compute the relative error of integral 2. It's in the order of 1 times 10 to the minus 12. Let's now try to integrate the same function over the unit disk. In this case, the integration runs from minus 1 to 1 in x, and the integration limits in y now depend on x. So we have to define two function handles, y_min and y_max, which determine the range of integration in y given a value of x. Since we want to integrate over the unit disk, these are the limits in y. Now we can again use integral 2 to obtain the approximative value of the integral. It's about 1.986, and we can do the same exercise in polar coordinates. In polar coordinates, we have to divide by the determinant of the Jacobian. So we evaluate the function handle fh in the polar coordinates r times cosine phi and r times sine phi, and we multiply with r, which is a determinant of the Jacobian of the transformation between Cartesian and polar coordinates. Integral 2 now gives an approximation of the integral in polar coordinates, and the relative error with respect to the integration in Cartesian coordinates is about 4 times 10 to the minus 10. Let's now pass to integration in 3D. Let's define a function f of 3 variables x, y, z with 2 parameters a and b. So this is a function definition. I convert it again to a function handle. I set a to 1 and b to 2. And fh is now the function handle with these values of a and b, which depends only on x, y, and z. We can easily integrate this over the unit cube. In this case, the limits are 0 and 1 in all 3 coordinates. We can also integrate over the unit ball. This should read integrate over unit ball in Cartesian coordinates. Now the integration limits in y depend on x, and the integration limits in z depend on both x and y, and they are implemented by these four function handles. So integration in x runs over the interval from -1 to 1, and given a value of x, the integration limits of y are given by these two handles, y min and y max, and given x and y, the integration in z runs over the limits given by these function handles, z min and z max. We are now ready to integrate over the unit ball in spherical coordinates. Very similar to before, we evaluate the function handle at the polar coordinates of the points in the ball, and again we multiply by the Jacobian of the transformation, which in this case is r squared times sine of theta. So this function is integrated over the unit ball by running the integration in r from 0 to 1, the integration in phi over the interval from 0 to 2 pi, and the integration in theta over the interval from 0 to pi. Okay, we can now again compute the relative error of the two integrals, one in Cartesian coordinates, the other one in spherical coordinates, and we see an error of the order of 10 to the minus 9.